Today I will describe the radiation with it is relating the number of photons interacting with a certain number of atoms. Last time we described about the Einstein's A and B coefficient. When we discussed about the Einstein's coefficient, we defined the number of observed photons per second. It is n times b times u, where the n1 is the number of atoms in the ground or lower state per volume, and n2 is the number of atoms per number of the excited state atoms per volume, and the spontaneously emitted photon is proportional to the n2 times a, and the number of stimulated emission photons per second is n2 times b times u. And right, with the same definitions and the same concept, we'll describe about this stimulated and spontaneous emissions of photons from an atom. Right. With the diagram, we can consider one photon coming in to an area where there exists a atom in the ground state, and then after the collision, photon disappears and atom becomes an excited state. That means number of photon is decreased by 1, while the number of atom in the excited state is increased by 1. And if a photon hits an atom in the excited state, then two identical photons comes out, and the excited state atom becomes a ground state atom. So number of photon is increased by 1, while the number of excited state atom is decreased by 1 by this stimulated emission. And when there is no photon comes in, excited state atom can decay into the ground state and photon comes out. And this is a spontaneous emission, but photon comes out to the random direction, so it does not contribute to the number of photons propagating to a certain direction. So in this case, we only consider number of atoms in the ground state is increased by 1, while the number of photons along a certain propagation direction is not increased. That's the physical picture of spontaneous emission of light from an atom. So last time we described about irradiance. It is C times U, whereas U is the number of photons per volume, and as each photon has energy h times mu, we can replace I with h mu times the number of photons per area, or photon flux. Right. So we'll use phi instead of I or U in the radiation. So replace U or I by using phi. Right. We consider a small volume in a medium whose thickness is dz, while its area is A. Then the number of atoms in this volume can be calculated by A times dz. And if each atom has opaque area sigma, then the total opaque area by atoms within this small volume is sigma times n1 minus n2 times A times dz. Let's see. Right, the ratio of blocked area or blocked photons is sigma times the total opaque area divided by A, or total the number of photons variation divided by total number of photons. Then if we divide A on both upper and lower part of this, then we can have n1 minus n2 times sigma times dz. So we have a simple relation about the variation of photons per propagation distance by taking dz to the left side and taking phi to the right side. So d phi over dz is minus n1 minus n2 times sigma times phi. So we describe the decreasing ratio of photons as it propagates through this medium as a function of distance is just minus n1 minus n2 times sigma times phi, where the sigma is the absorption cross-section of an atom. Right. Last time we derived the Beer-Lambert law like di over dz is equal to minus I times I, where alpha is the absorption coefficient. If we compare this with equation 2, right, if I replace I with the h mu phi, then we have the similar relation of d phi over dz equal to minus alpha times phi. And if we compare this with the equation 2, we can deduce that alpha is n1 minus n2 times sigma. So we obtain the relation between alpha and n and sigma. So we can replace the absorption coefficient, which is the macroscopic the parameter of absorption, with the actual number of atoms in the excited state and ground state, and the cross section of each atom with a photon. So 4 is the equation which describes the macroscopic absorption coefficient with atomic parameter of a medium. Actual cross section as a function of is a function of wavelengths, and the erbium atom embedded in a certain crystal is experimentally measured with this, and it's between about, it's in the order of 2 times 10 to the minus 20 per 20 centimeter square. That's the example of the cross-section sigma. Right. Here we replace the equation 2 with as a function of as a function of z. We'll replace this as a function of time because we only consider photon traveling to the z direction. So dz is just c times dt. So we replace dz with c times dt. Right. So we replace dz with c times dt. Then from equation 2 we have d phi over dt instead of d phi over dz is equal to c times n1 minus n2 times sigma phi. Similarly, we can with the relation between photons and the number of photons and the number of photon flux and the number of photons per volume, we can calculate the variation of number of photons per volume from the photon flux variation. That is u is h mu times phi, so du over dt is h mu times d phi over c times mu is equal to h mu times phi, so replace phi with u. Phi is equal to c over h mu u. So phi is equation 5 is replaced with u, then we have du over dt is equal to h mu over c d phi over dt, so it becomes h mu minus h mu times n1 minus n2 sigma phi. And this du over dt describes the variation of number of photons per volume due to the stimulated absorption and stimulated emission. Here, when we describe the absorption and stimulated emission, whenever there is a increment of photons or decrement of photon, there is an increment of atoms in the excited state. When one photon disappears or decreased, simultaneously one atom is excited. Same is true for this case, stimulated emission. If one photon number is increased by 1, the number of excited state atom is decreased by 1. And this is the spontaneous emission. We will not consider this. We'll consider this later. So there is a relation between the number of photons variation per second and the number of atom variation per second, and those are the same except the minus sign. So we just describe or obtained the number of photons per volume, variation of number of photons per volume with respect to time with this, then this ratio is exactly same as the variation of number of atoms per volume. So whenever there is a number of photons variation, that should be equal to the number of atoms in the excited state, or which is same as number of atoms in the ground state, because the number of atoms per volume is constant. So whenever there is an increment in the excited state atom, there should be a decrement of same number of atoms in the ground state. So dN over dt should be equal to minus dN2 over dt. It is same as the number of photons per volume divided by the right. So that is the number of photons per volume which is minus n1 minus n2 times sigma times phi. So we have the variation of the ground state or the excited state atom with respect to time with this new equation, equation 7. So equation 2, sorry, not equation 2, equation 5 describes the number of photons, variation of number of photon flux. Similarly, we have a equation for the variation of excited state atom or the ground state atom per second. So equation 5 and 7 are two rate equations which describes number of photon flux and number of excited state or ground state atoms of the medium. So those two are coupled, and those two are the two important equations to describe the interaction of photons and atoms. Right. Just before we disregard the spontaneous emission, and the effect of spontaneous emission can be easily added to the rate equation with this a number of ground state atom changing rate is the opposite sign of number of excited state atom, which is minus times n2 divided by tau. Tau is, in this case, is the lifetime of the decay. So this is this just describes the exponential decaying spontaneous emission ratio. So this is the equation 8 describes the spontaneous emission process. So by combining equation 8 and 7 and 5, 7 and 8, we have the dN over dt, which is equal to minus dN2 over dt, is at minus n1 minus n2 times sigma phi plus n2 over tau. Instead of using n1 and n2, n2 is the number of atoms in the excited state and 1 is the number of atoms in the ground state. Instead of using n1 and n2, we use delta n, which is n1 minus n2, the difference between the number of ground state and number of the excited state atoms. So we replace n1 and n2 with delta n and n. N is just n1 plus n2, total number of atoms per volume. And when delta n becomes negative, that means number of excited state atom is larger than the number of ground state atom. It's called the population inversion. And the medium acts like amplifier instead of absorption medium. So we replace the rate equation for the number of atoms, this, and the rate equation for the number of photon flux by using delta n and n. Then we obtain equation 9 and 10. That is, d delta n over dt is equal to minus 2 sigma phi times delta n minus delta n over tau plus n over tau. That is by replacing n1 and n2 with delta n and n in this equation. So, for example, if n1 is 1/2 times delta n plus delta n, and n2 is 1/2 of n minus delta n. So we replace n1 and n2 with this, and then we have this equation. But these are the two equations we like to use to describe the number of photon flux variation with respect to time, number of atoms in the ground state, or in the ground state minus in the excited state. So these are two coupled equations about the state of atom and number of atoms and number of photons. Which includes the stimulated emission, spontaneous emission, and those are the absorption as well. Equation 9 and 10 are the two equations we like to use. And in a steady state, dn over dt becomes 0 and d phi over dt is 0 as well. So we can consider the steady state condition, and then we can take dn over dt is equal to 0, and then we obtain that delta n is equal to n over 1 over 2 sigma tau phi, and we describe this as n over 1 plus phi over phi set. This is called, phi set is called the saturation photon flux, which is nothing but 1 over 2 sigma tau. So the saturation photon flux is a very important and measurable quantity, and this saturation photon flux can be represented by two atomic parameters: sigma, which is the cross-section of atom, and tau, which is the lifetime of the spontaneously emitted photons from an atom. So from equation 4, where is equation 4? Equation 4, absorption coefficient is n1 minus n2 times sigma, which is basically delta n times sigma. Then we obtained alpha with the n times sigma over 1 plus phi over phi set. as n times sigma is alpha 0, alpha, where is alpha 0? Right. Alpha 0 is when all the atoms are in the ground state. That means n2 is equal to 0 and n1 becomes total number of atom n. So alpha 0 is the absorption where all the atoms are in the ground state. So alpha 0 is n times sigma, basically. So alpha 0 is n times sigma, so we have the alpha as a function of phi becomes 1 over alpha 0 over 1 plus phi over phi set. So when phi is low, then we can consider phi is equal to 0, then the phi alpha becomes alpha 0, and as phi becomes phi set, it becomes 2, and absorption becomes half of alpha 0. So the saturation photon flux is the photon flux where the alpha absorption coefficient becomes half of its original the original absorption coefficient. That's the physical meaning. So we can also calculate calculate population inversion delta n as a function of photon flux phi, delta n as a function delta n as a function of photon flux, that is n over 1 plus phi over phi set. So if we divide this delta n with n, then it becomes 1 over 1 plus phi over phi set. So this is this curve just show how if we consider this n over delta n over n, so that's a population inversion, normalized population inversion, then it becomes almost 0 as the photon flux is increased from 0 to infinite, basically. So when photon flux becomes infinite, absorption coefficient becomes 0. Same is true for the population inversion. When phi becomes infinite, delta n becomes 0. So the number of photons in the excited and number of photons in the ground state becomes same when a lot of photons comes in simultaneously. That's the result of equation 12 or 11, and that's what we can observe in real experiment. This how it happens. So if the intensity or photon flux becomes the photon saturation photon flux, then the absorption becomes 1/2 of its original. That's what it is. If phi set, phi becomes phi set, and phi is related to the irradiance I with the h mu times phi is irradiance I, so we can always convert the irradiance with the photon flux phi, and when irradiance becomes, so the irradiance set is equal to h mu times phi set. So here the irradiance set is equal to h mu times phi set. So if we increase the intensity or increase the photon number, then when photon number becomes phi set, then its absorption or population inversion becomes 1/2 of its original uh, population inversion or the original absorption coefficient. Post-propagation through a medium can be considered with this cascading effect. If delta Z is very small, we consider initial photon flux coming in, then it modifies number of atoms in this small slice of a medium. Then the throughput or the photon number is varied by the interaction of photons and medium. Then we can consider this reduced photon number to the input to the next slice of a medium, and so on. So we can cascade this to consider or simulate a thick absorption medium. And you need to numerical calculation to calculate each variation of photon flux and the number of the excited state atoms versus the number of ground state atoms, and we cascade this to solve a certain volume of a medium. Interaction of photons with a certain volume of a medium. And we also consider the Lorentzian line shape function for simple absorption medium, and we obtained the Lorentzian or the absorption coefficient, as the absorption coefficient is related to the number of sigma times n is equal to alpha. We described this, we have derived this before. Alpha is n times sigma. It's basically delta n times sigma, but when there is no excited state atom, then delta n becomes n. So alpha is just becomes n times sigma. And with this relation, we have the as we derive the alpha as a function of omega, at the beginning of this course, we can derive the spectral variation of sigma as a function of omega. It is basically Lorentzian shape. It is just a 1 over n times omega over c, imaginary part of chi. And we have the analytic expression for chi, which is like this. And that's the reason why the sigma becomes a function of frequency. For a certain the spectral width, we integrate all the sigma, and that becomes the transition cross section S. Right. So that's these are few numbers for the transition cross section S for the CO2 laser gas and neodymium doped ion in the neodymium YAG crystal, and so on. Those are basically in the range of 2 to 10 to the minus 20 to 10 to the minus 13 centimeter square. Right, the last concept we'd like to consider is the pumping process. Pumping is the process to change the ground state atom to the excited state atom. Those are basically done by flashlight or LED or pump LED pumping. This is the optical pumping, and by colliding electron, the accelerated electron, to an atom, we can pump the, the laser medium. And by chemical reaction also, we can make the atom to become a excited state. Those are pumping process, and without considering actual mechanism, we just represent this pumping process by using the pumping ratio R. That is, changing the number of atoms in the ground state with respect to time is just minus R, and that is same as the number of the number variation in the excited state atom. So this is to have the conservation of the total number of atoms. We always have dn over dn1 over dt is equal to minus dn2 over dt, and the variation of this is represented by the pumping ratio R. So we have we need to consider three cases: absorption and stimulated emission, that is equation 7, and spontaneous emission, which is described by equation 8, and pumping is described by equation 15. And if we consider all of these the dynamics all the time, then we just add this whole process together. And if we add 7, 8, and 15, 7, 8, and 15, we have a one rate equation: dn1 over dt is equal to minus dn2 over dt is equal to minus this term, then this term, and this term. It is the summation of this and this and this. The rate of n1 over dt, dn1 over dt, is equal to this times this minus the. We should replace this plus and this plus, and we should add this. So we should add this one plus this one instead of minus, plus this one. So we have the n1 over dt is this times plus this and minus this. And if we replace delta n1 and n2 with delta n and n, then we have the rate equation for delta n and phi as well. So here we d phi over dt is all the same, because pumping process does not add or decrease any photon numbers, or spontaneous emission does not add any photons to a certain direction, because as I mentioned, the emission direction is random, so it does not contribute to photon propagating to the z direction. It contributes a little bit, but we just disregard this small portion of the randomly emitted spontaneous emission to the direction of photons propagating along the z direction. So the equation 5 does not change with the pumping or the spontaneous emission. So at the end, we have two rate equations describing the dn over dt, d delta n over dt, and d phi over dt. It describes the spontaneous or absorption and spontaneous emission. Stimulated emission, this is the contribution term by the spontaneous emission, and this is by pumping. This is only for the stimulated emission and the absorption. So equation 17 and 10 are the two equations we like to solve later. Right. When for the state, when there is only pumping without any photon input, from equation 17, delta n over dt is equal to 0, then we have and input photon density is 0, phi equals 0, then we have this simple equation delta n is n minus 2 tau times r. So population inversion delta n is n minus 2 times tau times r. When the external photon number is not 0, then we have in the steady state we have this 17 becomes 0, then we have delta n is equal to this, and we can represent this with the phi set as well. So delta n is delta n0 1 plus phi over phi set, and delta n0 is n minus 2 tau r, n minus 2 tau r, when there is no photon flux. So those are the two rate equations we need to solve to describe photons and the number of atoms in the ground state or excited state. And those are the two equations we need to solve to describe the dynamics of photons or amplification or absorption dynamics of photons through a medium. That's about it.